Hello and welcome to today's discussion or video lecture presentation on JFET characteristic curves and operation. So once again, here is our JFET transistor. So remember we have the gate, the source, the drain. Here's our channel right here. So here's our diode symbol. So the tip is the minus end. Since the minus end points towards the channel is negative. So this would be an example of an N-channel JFET. We're going to look now at some similarities and, well, we're going to look at some main differences between a bipolar junction transistor and a JFET. So here's difference number one. A JFET, put that in here. A JFET operates in reverse bias, unlike a bipolar junction transistor where the base and emitter must be forward biased. So notice here that we have the base of our diode symbol is plus. To have a reverse bias arrangement, we would need a minus terminal of our DC power supply, and we could call that VGG, connecting to our N-channel JFET. And the reason is, once again, because here's our diode symbol right here. The base of that diode is plus. VGG would therefore have to be minus, because this is reverse bias, minus the plus connection between our voltage source and our gate terminal here. Here's another big difference. As the gate to source voltage approaches zero, you'll get a larger drain current. So if we have a gate to source voltage equal to zero, so if we put grounds on the gate and the source, because that would be zero, we would achieve maximum drain current, and we're going to see that in charts in the upcoming minutes. So this is at its strongest. The drain current is the highest when our gate to source voltage is zero. Unlike a bipolar junction transistor, where as you increase the base voltage, or the VBB, which would be analogous to this end of a bipolar junction transistor. As you increase VBB, then you get more collector current and emitter current going through your transistor circuit. Field effect transistors have high current and low electrical noise. And the conduction, like we said, is controlled by an electric field rather than a silicon PN junction as found in a bipolar junction transistor. So those are several main differences between a junction field effect transistor and a bipolar junction transistor. So with the JFET, if your gate to source voltage is zero, we achieve the maximum drain current known as IDSS. So whenever you see a VGS equal to zero, you always associate it with achieving maximum drain current. Your DC power supply voltage at the gate will set the reverse bias voltage. So remember what forward bias and reverse bias is. Forward bias is when you look at the relationship and polarities between your power supply and the polarity of your diode. They have to be the same. You need plus to plus polarity. The reason being is you have, for a diode, you have this minus end here, which is the minus end of your diode. That's where all the electrons, which are negatively charged, are hanging out at. The minus sign of the voltage source, the minus polarity of the voltage source, will repel the electrons, and as long as your as long as your voltage source is greater than 7/10 of a volt, which would give our electrons enough energy to jump that PN junction, then they jump over to the waiting holes or vacancies, which are noted as positive polarity. So now the electrons are over here. The negatively charged electrons will be attracted to the plus end of the power supply. And now we're promoting current flow in a single direction. So this is forward bias, and that's the reason why the polarities have to match. In reverse bias, we basically widen the PN junction found in a diode. Because here at the base of our diode symbol is our waiting holes or vacancies, which are positively charged. So they're going to be attracted to the minus end of the power supply. Now at the minus end here, the cathode end of our diode, we have a waiting electron, specifically speaking valence electrons, because they have the loosest attraction to the nucleus of the atom, so it doesn't take as much energy to break their orbit from an atom to go into another orbit of a neighboring atom. So the negatively charged electrons are going to be attracted to the positive end of our DC power supply. So now here is a promotion of current flow in two different directions. So this will basically create an open. So you're not going to get any current flow. This is reverse bias. So the point I wanted to show here was reverse bias is when the polarities between the source and your either transistor or diode are minus the plus or plus the minus polarities, and forward bias, the polarities between your transistor symbol and your voltage source have to match. That's the rationale behind it. So notice here the base of the diode symbol is positive. So in order to have reverse bias, your VGG, you need the negative terminal going to the base of our triangle here. So let us look at our first characteristic curve. So what's going to happen is, now notice I have an ID, drain current, versus a VDS characteristic curve. This is analogous to having, for a bipolar junction transistor, IC versus VCE curve. So what's going to happen is, as you decrease your gate to source voltage, you're going to get an increase, a linear increase in your drain current. This is called the ohmic region, which is right here. Then there's going to be a certain point in time where we achieve maximum drain current because the gate to source voltage is equal to 0. Now we achieve something called the pinch-off voltage, or VP. VP and VDS are the same thing. So basically we're labeling a value of VDS as VP, saying, hey, this is where we're achieving maximum drain current. So right here is where we end up getting maximum drain current, known as IDSS. Now from this point, you can't get any more 0 than 0. So we're going to end up with constant maximum drain current. So right here is called the constant current region. Then there's a certain point in time where if we increase our drain to source voltage enough, then we're going to get an avalanche of drain current, which will basically ruin or destroy your junction field effect transistor. So here is where you'll end up getting avalanche breakdown. And here's the point where you would damage the JFET. So very important to remember that the quantities that you want to watch out for is when the gate to source voltage is 0. Then you are at maximum drain current. If you're at maximum drain current, then you're at the pinch-off voltage, which is a form of the drain to source voltage. A very important, I'll show this first before I go over this statement. So let's look at it, let's look at this in another way. So I'm just going to show some minus gate to source voltages here. We'll pretend for this particular JFET that we end up getting a gate to source voltage of minus 4 volts. This is our cutoff. So this is our VGS cutoff. In this example, minus 4 volts. This changes based on the type of JFET that you select. So this right here varies. So right here, notice when we're at VGS cutoff of minus 4 volts, since we're right on the x-axis, the Y component, which is drain current, there's no Y component if you're directly on the x-axis, so you have 0 drain current. So at VGS cutoff, your drain current is 0. At VGS cutoff, which is right here, your drain current is 0. So now as we negatively decrease our VGG, or our gate to source voltage, as that decreases, it gets to 0. Now we are at IDSS, the maximum drain current. Now you can see that this isn't a linear line here. So you can't solve for your drain current like we would for the collector current of a bipolar junction transistor. BJT transistor circuit is linear, and we could solve it using linear equations. Here, to calculate the drain current at any point in time, based on what our VGS is. So if I want to find the voltage or the drain current here, or here, or here, or here, I use this formula. Drain current is approximately equal to the maximum drain current times the quantity, 1 minus the gate to source voltage. So that would be the gate to source voltage at one of these points here, over our VGS cutoff squared. Now another important relationship is that the VGS cutoff value and the pinch-off voltage are the same in magnitude but opposite in direction. So it's knowing these points right here, having them in the back of your mind, that could help you solve a good chunk of these JFET circuits. So when VGS is equal to 0, you're at maximum drain current. And when you're at maximum drain current, you're at the pinch-off voltage, which is a form of VDS. Also, VGS and the pinch-off voltage are the same in magnitude but opposite in direction. So for instance, if you're given, in the problem, it says VGS cutoff is minus 5 volts. Then therefore, the pinch-off voltage will be at 5 volts, which is a form of VDS. So if I'm at the pinch-off voltage, I know I'm operating at maximum drain current, and usually that'd be a given in your problem. So now you could use this to solve the JFET circuit. Now in the next video, we're going to start looking at some examples and applying these charts and what we just went over to the problems that we're going to be looking at with JFET circuits. Thank you for listening in, and I hope you found this video useful. Have a good day, and thank you.